3.6, rational functions. We know that a rational function r of x equals p of x over q of x, where p and q are polynomials. We assume they have no factors in common. And even though each one will be different, it will take the basic form of the base function f of x equals 1 over x. And you see that there's two branches of the hyperbola. This is a hyperbola. And they get really close to each axis, but they will never hit it. These are called asymptotes. So there are vertical and horizontal asymptotes. The line x equals a is a vertical asymptote of the function y equals f of x if y approaches infinity or y approaches negative infinity as x goes to positive a or negative a. The line y equals b is a horizontal asymptote of the function y equals f of x if y approaches d as x approaches infinity or x approaches negative infinity. So our rules for graphing is we need to find the domain. And we find the domain by setting the denominator equal to 0. And we're going to be using interval notation, of course. We're going to find the horizontal or slant asymptote. And it's going to be of the form y equals. And to do that, we divide the numerator by the denominator. We're going to reduce the function, factor and cancel. We're going to find vertical asymptotes, which will be the equation x equals. And what you do is you take the remaining denominator equal to 0. We'll find the x-intercepts, and we'll find the y-intercepts. To get more points, we're going to make a table based on the asymptotes. We want some on the left of the asymptotes and the right. So we're going to graph by hand f of x equals x squared minus 1 over x. So our domain said to take the denominator and equal it to 0. Solve the denominator. So x equals 0, but we know that's not true. It cannot equal 0. So interval notation would be negative infinity to 0, union 0 to infinity. So we see x cannot equal 0. We're going to put our asymptote a dashed line where x is 0 because we know our graph will never cross this. For our horizontal horizontal or slant asymptote, we divide. So we have 2x minus 1 dividing by x. We get 2. And negative 1 is our remainder, which doesn't matter. So our horizontal asymptote occurs at y equals 2. So we go to where y equals 2 and put a dashed line through it. So now we have our horizontal asymptotes. It says to reduce, cancel out factors. There is nothing we can cancel, so it's just 2x minus 1 over x. our vertical asymptote, which we found from our domain already, is x equals 0. Already have that put in. To find the x-intercept, we take the numerator, 2x minus 1, set it equal to 0. Solve for x. It's going to be 1/2. This is a point on the x-axis. It's an x-intercept. So we go to where x is 1/2, and we can put a point. We know it's going to pass through here. That also tells us one of our branches is going to be in this quarter, and therefore opposite as well. Now to find the y-intercept, we evaluate f of 0. So 0, 2 times 0, minus 1 over 0. Well, it's undefined. We can't divide by 0. So there is no y-intercept. And that makes sense because it was an asymptote. Okay, so now we need to get more points by making a table. We're actually going to need to make 2 tables because there's 2 branches. So if we work left of the vertical asymptote, we're going to go -3, -2, -1, and see what we get out. So for -3, it goes 2 times -3, minus 1 over -3. It will be -6 minus 1, -7 divided by -3. That's 7/3, which is roughly 2.3. So we get a point, -3, 2.3. -3, 2.3. Plug in -2, 2 times -2 minus 1, minus 3. -4 minus 1 over -3 goes to 5. Oops, that should be over -2. 5/2, which is 2.5. To 2.5. -1 goes 2 times -1 minus 1 over -1, and that comes out to 3. -1, 3. If we were to do -1/2, we get 2 times -1/2 minus 1, so that goes to -2 over -1/2, goes to a +4. So we see it's very close as x approaches -infinity, y approaches 2. So this is one branch. To get the second branch, we need to start with 1, 2, and 3. So 2 times 1 minus 1 over 1 goes to 1. So we get the point 1, 1. We already had our x-intercept of 1/2, 0. 2 goes to 2 times 2 minus 1 over 2 goes to 3/2, 1.5. So 2, 1.5. 3 will go 2 times 3, 6 minus 1, 5 over 2 over 3, which gives us 5/3. Not quite 2. And we connect dots as such, getting close to the asymptotes but never hitting. We're doing a graph by hand. F of x equals x over x squared minus x minus 2. So our domain, we take the denominator, set it equal to 0. So we factor x minus 2 times x plus 1. So we get x equal 2 and negative 1, but they cannot be that. So we break up our denominator into negative infinity to negative 1, union negative 1 to 2, union 2 to infinity. Our horizontal slant, we had to divide x squared minus x minus 2. Oops, nope, wrong way. Numerator in the box, dividing by the denominator. But we see we're dividing by a larger power than x. Nothing can go in. So our horizontal slant occurs at y equals 0, because you cannot divide this. So we draw in our line y equals 0, which is the x-axis. Now we are looking to reduce, so our original problem, x over x squared minus x minus 2, becomes x over x minus 2 times x plus 1. We factored, but we can't cancel anything. But we're going to use our factored form to find our vertical asymptotes. X minus 2 equals 0, x plus 1 equals 0. So we get them at 2 and negative 1. Same thing as our domain restrictions. Our x-intercept, we just set our numerator equal to 0, x equals 0. So we have the point 0, 0 here in the middle. And for our y-intercept, we find out f of 0. It's going to go to 0 over negative 2, which is still 0. So same point. Now we see that the graph is divided up into 3 sections, vertical, from left to right. So we're going to need 3 tables. So let's go with -4, -3, -2. If we plug it in, it's going to go -4 over -4 minus 2, -6, times -4 plus 1, -3, goes to -2/9. Okay, -3 is going to go -3 up top, over -5 times -2, goes to -3/10. -2 is going to go -2 over -4 times -1. And that goes to a -1/2. So we see how the curve is going. Now we need the middle section. We already got 0. We need 1. We go 1. We get negative 1/2. Now that's not enough for us to see what's going on, so we also need to work out positive 1/2 and negative 1/2. When you work these out, I'm running out of room, so I'm not going to show you working it out. You're going to get for 1/2 negative 2/9. And for negative 1/2, you are going to get 2/5. So what's happening is it's a curve that changes concavity at the middle. Alright, and our third area. We need values of 3, 4, and 5 for our table. Three is going to go to 3/4. 4 is going to go to 2/5. And 5 is going to go to 5/18. So we can draw our hyperbola. Even with more sections from left to right, it's still the last two are opposites.